You know, we're surrounded by liquids all the time, right? But have you ever really stopped to think about what's going on inside them? It turns out there's this incredible, invisible battle happening, a constant push and pull that decides everything. And today, we're going to pull back the curtain on that secret world.
And it all kicks off with a super simple question you've probably asked yourself in the kitchen. Why is it that when you pour honey, it kind of crawls out of the jar, but water just dashes out in a big splash? The answer to that one little question? Well, it gets to the absolute heart of how all liquids work.
Okay, so there's a sciencey word for this, and it's viscosity. But all that really means is how much a liquid resists flowing. So something with high viscosity, like honey or that thick motor oil, its molecules are all tangled up, kind of holding on to each other, which makes it move super sluggishly. On the flip side, you've got your low viscosity liquids. Think water or gasoline. Their molecules just slide right past one another. No problem. Easy peasy.
So, what's really going on down there at the molecular level? What's causing that difference? Well, it all boils down to this constant tug-of-war between two super important forces. Let's dive in and meet them.
All right, first up, you've got cohesive forces. The best way to picture this is like team spirit for molecules. Seriously, it's the force that makes identical molecules want to stick together. So water molecules stick to other water molecules, honey to honey, they're all on the same team trying to stay close.
And then on the other side of the coin, you have adhesive forces. This is the attraction between different kinds of molecules. Adhesion is the reason a raindrop sticks to your window or why you get that little bit of milk clinging to the side of your glass. It's the liquid molecules sticking to a totally different surface.
Okay, so now that we know about these two forces, this is where things get really cool. Because when they start to interact, they create some truly mind-blowing effects. And the first one we're going to look at is what gives a liquid its surprisingly tough outer skin.
Yeah, that's right, a skin. It's often described as being like a stretched rubber membrane. Think about it. Deep down in the liquid, a molecule is getting pulled on by its neighbors from every direction, up, down, left, right. It's all balanced out. But for a molecule right on the surface, there's nothing above it, so it's only getting pulled inwards and sideways by its teammates below. This massive, constant inward pull is what creates that tight, elastic layer we call surface tension.
And this tension isn't the same for everything, not even close. It varies wildly from one liquid to another. Water, for instance, has a really high surface tension because of the strong bonds between its molecules. But then you look at something like mercury. Wow. Its cohesive forces are so incredibly strong that its surface tension is just off the charts. That's why it pulls itself into those tight, almost perfect little silver balls.
So, what does this tough skin actually do in the real world? Well, it's the reason tiny insects like water striders can literally walk on water. It's what pulls raindrops into that classic spherical shape, trying to make the surface area as small as possible. And get this, if you do it just right, it's even strong enough to float a steel needle on top of water. That's the power of cohesion, right there.
But, hang on. Cohesion is only half the story, right? If water molecules are so into sticking together, then why does water seem to climb up the side of a glass, but beat up into little balls on a freshly waxed car? Now we get to the really good part, the battle between the forces.
It all comes down to which force wins, adhesion or cohesion. So for water in a glass, adhesion is the clear winner. The water molecules are actually more attracted to the glass than they are to each other. So they wet the surface and start climbing the sides, which gives you that classic U-shape, that concave curve. But with mercury, oh, no contest. Cohesion is the undisputed champ. Its atoms are so obsessed with each other that they pull away from the glass, forming that little dome shape, that convex curve.
So, we've seen these two forces fight it out. But what happens when they actually start working together? Well, that's when something truly incredible happens. They can team up to defy gravity itself.
This amazing thing is called capillary action, and you've seen it 1,000 times, every time you clean up a spill with a paper towel. It's a simple three-step process. First, adhesion goes to work, pulling water molecules onto the tiny fibers of the paper towel. Step 2, cohesion kicks in. Those first molecules then pull their buddies along for the ride. And step 3, the climb. This whole process just repeats itself, creating a chain reaction that pulls the liquid right up the towel, fighting gravity the whole way.
And look, this isn't just some cool party trick with a paper towel. These forces are absolutely critical to life as we know it and to a ton of our technology. let's take a look at just how much they shape our world.
I mean, this stuff is happening everywhere, all around us. Capillary action, that's the engine that's pulling water and nutrients all the way from the soil to the very top of the tallest trees. In medicine, it's what lets a tiny glass tube suck up a blood sample, almost like magic. Heck, it's even at work inside your own body right now, helping to spread tear fluid to keep your eyes lubricated. These invisible forces have a huge, profound impact on everything.
So think about it. From the slow, gooey crawl of honey to an insect skating on a pond, all the way to the life-giving water in the leaves of a tree, it all comes down to that simple push and pull between molecules. We've just taken a peek at the unseen forces that govern the world of liquids. And that kind of leaves you wondering, right? What other invisible forces are out there, shaping your world right now?